I would like to introduce our next speaker, JP Vasseur, who is a Cisco Fellow and Vice President of Engineering in AI. He boasts an impressive 32 years career, marked by the design of groundbreaking Internet technologies, including routing, MPLS, traffic engineering, switching, IoT, and security. JP has been leading AI for Cisco networking for the past 12 years, leading to the development of 3 groundbreaking AI networking products. He is joining us remotely today to present, is there a genuine need for ML AI in the Internet and networking? Welcome, JP.
I'm very glad to be back at NANOG. And indeed, I just have one question for us today, which is the question you just mentioned. All right, so I would like really to step back a little bit. As you said, we have been working at Cisco for about 12 years on the use of ML AI for networking. I've got this question, which is totally fair, very often on whether we really need to have ML AI for networking. So what I'd like to do today is to review multiple networking areas, such as wireless, line switching, SD-WAN security, quality of experience, multi-domain troubleshooting, optical and 5G, and so on and so forth. And on purpose, the goal of today is not to go and discuss about machine learning AI technologies, is not to discuss about Cisco products, and I will now a little bit to the use case of networking. I won't be talking too much about collab and security. Both are areas where machine learning AI is used pretty much everywhere. But for today, we're gonna talk about networking technologies. So I just told you that I will not be doing any kind of ML AI technology review. Still, very, very quickly, you might have seen similar slides in the past. There are multiple ways of doing learning. Some are referred to as unsupervised, when we try to find a hidden pattern in the data. Other ones are supervised learning, who have been used for a long time, especially in vision, for classification as well, and regression. When you have labeled data and you try to train a machine learning algorithm to make a given task, such as classification. More recently, we've been using self-supervised learning, which is a very promising one. And of course, reinforcement learning, which is one of my preferred ways of doing learning, which I believe is the closest one to biological systems. And of course, everybody knows now about large language models that make deep use of machine learning, obviously, and neural networks. There are many topics related to ML AI, such as explainable AI, different kind of technologies that allows to train an algorithm for a given task, and transfer learning is called transfer learning by definition, the ability to do multitask learning, and so on and so forth. But again, the goal is not to discuss about these technologies today. What I'd like to start with is a fundamental principle we have been applying at Cisco for a long time, which is that I don't believe we should start with technology. And that's exactly what I'm going to do for the next hour. I've seen so many beautiful technologies that just died because people started to work on the technology with the hope of finding a good use case. I've been doing exactly the opposite when designing ML AI-based products. I absolutely believe that technology is a mean, not an end. And so I strongly believe that we should first start with some use cases, and then knowing what ML AI can do, see how they could be applied to it. And I think there's a role for looking at science and technology, and this is really fundamental research. But of course, today I'm going to take a industrial hat, I would say. So let's start with wireless networks. And I'm not going to talk about 5G today, but mostly Wi-Fi networks. So let's have a look at Wi-Fi network without machine learning AI. So you guys know that very well. It's a fairly complex end-to-end problem when you look at Wi-Fi. You've got, of course, STA side, with the clients. Then you connect to access points. Then you've got technologies to connect to local or cloud-based wireless controllers with CapWap tunnels, for example. And of course, when you connect to the Wi-Fi network, you're going to go through the internet. And in some cases, you may need to have to connect to different kind of servers for authentication, configuration, addressing, and you name it. And of course, your traffic is going to reach some external servers and SaaS-based application and so on and so forth. So now, when you have to design such a system, there are a lot of complicated use case, I would say. There are some KPIs that are very well known. So for example, the time it takes to connect, the probability of failure when you roam from one AP to another AP, and there are other KPIs that are extremely important for us, networking people, such as the throughput. And this is usually where people complain when they complain about Wi-Fi sometimes. They complain about poor quality of experience because they believe that the throughput is not high enough. So how have we been looking at it from a throughput standpoint? Well, it's very difficult to know if the throughput you get is insufficient, I would say, because it depends. It depends on the environment, the signal-to-noise ratio, the RSSI, the number of clients, and so on and so forth. So when you're designing a network and then you operate the network, and what you're trying to determine is whether the throughput is what should be expected or not, this is a very hard question to answer. So what I did when I started to work on the design of the AI-based products, I thought, is there a way to set thresholds? And this is what we have been doing for many, many years, right? So what I'm showing you on the right-hand side are multiple networks, and we looked at the 24-hour average throughput for multiple access points. So each column is an access point. And what you see is that some access points, they provide really good throughput all the time. Other ones, it tends to vary because it could be related to issues such as simply the number of clients connected to it or things like that. And you see pretty much all of the patterns. So when you see these kind of patterns and you want to monitor the Wi-Fi network and you don't have a system that is capable of learning, then what you have to do is to start playing with multiple thresholds. And the same applies to many kind of KPIs. If you look at onboarding, here what you see on the plot, each line corresponds to a different network. And this is really, real life deployment networks in this case. So if you look at these networks, what you can see is that the percentage of onboarding failures can vary between 5 and 35%. And there are good reasons for that, simply because the deployment is different, the level of congestion is different. And if you look at the onboarding times, we have networks where we're talking about half a second to connect. Other networks, this is in general more than 4 seconds. So how would you want, as a Wi-Fi administrator, to come up with threshold that you would statically configure, and by crossing the value of the threshold, you raise some alarm and say there's something wrong about the time it takes to connect to the network or the percentage of roaming, for example, roaming failures. So what this shows you is really that there is a need to have a mechanism that allows you to learn what should be expected without having to go through static configuration. That's really, a very good sign that AI/ML may be a good candidate for that. And I just showed you, very few KPIs. There are many other ones, such as the excessive DHCP timeout and failures, AAA authentication times, application experience, you name it, right? So we're probably talking about dozens of KPIs that you may want to monitor. Now think about it, when you have thousands of access points and dozens of thousands of clients, and you've got potentially dozens of KPIs, there is no way a network administrator could go and manually configure static threshold from multiple locations in the networks. And as a matter of fact, you also may need to take into account, the time of the day and so on and so forth. So now, what does that mean? Well, it means that if you take advantage of the learning mechanism, such as machine learning, machine learning, for example, you could have a system that is capable of learning what should be expected or not. And this is really a very simple use case. When you see that what we had been doing for many, many years, which was very cumbersome, and you know what is happening when you play with threshold. If you configure too low, you have too many false alarms. I wouldn't say false positive, it's not a classification problem. And if you make it too high, then you have the risk of missing some real issues. And so machine learning can be used there for many, many reasons. Cognitive issues, you may want to find out that your system is not performing as expected, but you want to have a model that is capable of telling you that automatically. You may want to look at the trends as well. What do I mean by trends? It's when you start looking at a given KPI over a long period of time, maybe days, maybe weeks, maybe months, you may want to detect that all of a sudden you have a slight deviation. So this is what we call trend, if you will, over a long period of time. And in some cases, you may want to have comparative analytics. How is my network doing compared to similar networks? Of course, you want to compare apple to apple. Okay, so this is what the system does for you. So here I just took the average duration in seconds, the KPI I was talking about before. What machine learning can now do is to take into account multiple parameters, multiple variables that we call input features, and then tell you what you should expect in terms of average onboarding duration for a given location, considering multiple characteristics of a network. This is the green band that you see on the screen. In other words, that green band has been computed by machine learning algorithm, and by monitoring this KPI in real time, when you fall outside of the green band, it means that you have an anomaly. This is as simple as that. And as you can see on that simple example, there is no way you can have a static threshold that, by the way, would have to be dynamic, that would do the same job for you. So I'm just showing you a few examples. I just chose two of them here. You look at some real-time anomaly detection. It was a context of a retail, and it was a drop in the throughput for collaboration applications. So in this case, we have a model that is capable of telling you what should be the expected throughput for a class of application known as collabs. So what is the benefit in this case of using ML/AI? And back to my question, do we need ML/AI? Well, in this case, very clearly, what it allows you to do is not only to avoid having to configure hundreds, if not more, thresholds statically, but even more importantly, it's going to cut the noise. And so instead of having a huge amount of alarms, unless you have a very loose configuration of a threshold, in which case you're missing also a lot of issues, you have a system that learns on the fly, dynamically taking dozens of parameters into account. And we did some math in this case. Again, it's just one example, taking a dozen of customers over a 3-month period. In this particular case, we could show that there was a 98% reduction. The number is not very important. What is interesting is really the order of magnitude. Of course, that's not sufficient. You want to use machine learning for anomaly detection, but of course, when you see the anomaly, you want to understand the root cause. So I'm just giving you an example where the system is not only capable of raising anomalies, learning dynamically for all of the access points you have in your network, but you may also want to find the root cause. And then, what we found interesting is that sometimes anomalies are subjective, and you show the same anomaly to two different Wi-Fi experts. One of them will find that the anomaly is very interesting. The other one may say, well, it's not super relevant. So in this case, I just wanted to raise that, to mention that it could be interesting to have a feedback loop, according which the network, the Wi-Fi administrator may want to provide a feedback to the system and say, I don't want to see this kind of anomaly. And you could have a system that is going to filter on the fly the type of anomaly being raised. Just a quick note about correlation and causation. I know you might have seen this the similar slide for a long time. People tend to really, when they say RCA, root cause analysis, for the most part, they refer to correlation. And we need to be very careful about that because you can find variables that are highly correlated and still one is not the cause of the other one. Mathematically, we can demonstrate, it has been proven that unless you intervene on the system, you cannot really check the effect of correlation. But I wanted to mention that because sometimes there is a lot of shortcut and people keep talking about causation, although they mean correlation. Okay, I just wanted to take another example in the context of IoT. So, and spoofing attack detection. So in this case, as you know, in the IoT landscape, it's very common to have devices for which you may wonder, the type of device they are. And so one aspect is, of course, to say, that's okay, I'm going to use a static rules, and you come up with a lot of rules, looking at the OUI of the MAC address, you can look at the user agent or DHCP option, you name it. So that's also a very good example where you could be using machine learning. So I just took an example for you. So in this case, you may want to use some unsupervised techniques so that the algorithm may have a look at a lot of endpoints for which the device is unknown and try to group together devices that seems to be similar. It's called the clustering technique. That's something very well known, and there are many algorithms to do that. It may not be as easy as you think, because if you look at a given device, you may want to characterize the device based on a number of attributes, in which case what is shown as a 3D space may end up being made of hundreds of dimensions. And when you have 100 of dimension, and you want an algorithm that will group together points that are close to each other, you need to define the distance. And the distance is something that needs to be handcrafted, if you will. So I'm just showing you some examples of what we did in this case, but we came up with a way to determine what is a good distance, and then the rest is fairly simple. You can use an algorithm like dbScan to look at the density of the points. But this is extremely performant and efficient to do it that way, because when you have thousands of devices that are unknown, instead of going one by one and put a rule in a static fashion, you may want to use machine learning to regroup devices that are known as being similar. And then all you need is to have a look at a few samples in each cluster. And once you have a label, you can train another machine learning model to come up with the rule automatically. All right, so this is yet another example. And that's not the end of it, right? So the next one is about spoofing attack. There are many ways to attack, and do spoofing attack. It goes from MAC spoofing to probe spoofing to malware. The example that I wanted to mention is, again, that you could come up with static rules according which, if you look at a device that is being connected, you may want to use these rules to say, the device claims to be a camera, it doesn't look like a camera. But you can understand how difficult and cumbersome such an approach could be. In contrast, if you want to use machine learning, the way to do it is to train an algorithm that has seen a lot of examples of behavior of a camera. So in this particular case, we are using NetFlow IPFix records. And what you show to the algorithm is a lot of examples of a camera, and you ask basically to do a classification task using an SVM or whatever you want, a neural net if you want. And basically the output of the algorithm is to say there's a probability X that this device that claims to be an IP camera is indeed an IP camera. And this is extremely powerful because then you can decide what to do. So if a device claims to be camera, but based on the behavior, the system finds out that it doesn't look like the behavior camera, you put under quarantine, for example. And that's something you can do as well. So this is yet another example. I'm not showing that slide today, but there is a slide that shows you the type of rule you would have to come up with in order to do the same tasks as a support vector machine doing classification. And I can guarantee you that you don't want to come up with this kind of rule because they are awfully complex. The job of the algorithm is exactly to learn this kind of rule and then come up with that rule automatically. All right, so this is not the end of it. I've got more for you. This one is to me, and I think this is very appropriate for Nanog audience, this is about the internet. So as much as we love the internet, all of us, the internet has been reactive for 35 years. What do I mean by that? What I mean is that, first of all, the detection of an issue is usually characterized by the liveness of a path. And for that, you may want to use routing adjacency, fast keep alive, you name it. So basically, you are only looking pretty much at the layer 3. Then the second issue is that you need to wait until you detect the issue so as to find an alternate path. And the alternate path, depending on the layer, could be a pre-provisioned backup path using 101, 1 by n, 1 plus 1 in the optical domain, for example, or even in packet domain as well. You may want to use MPLST fast reroute, path protection, link node protection, with or without bandwidth protection, you name it. So there are many, many techniques, and it used to take minutes to converge, seconds. Now we are talking about milliseconds, and all of that can be done, on the fly as soon as we detect the issue. But again, there is no learning strategy. And what I mean by no learning strategy is that the protocols, they do not adapt dynamically to the system. Actually, if you look at the human brain, and I don't want to bother you with one of my passions in life, which is neuroscience, but the human brain has the ability to learn, to predict. This is one of the most powerful predictive engines on Earth, and of course to plan as well with prefrontal cortex. So the idea was, can we start designing a system that will be able to predict issues before they happen? And I'm sure you're going to react, as many people did react when I presented this idea in 2019 and said, oh no, the internet is highly unpredictable. And if you try to predict, you will make a lot of, false positive, if you will, and then there will be a lot of issues and so on and so forth. There is no way you can replace reactive systems. And this is true. I'm not claiming that we can replace reactive mechanism, but I do claim that it is possible to model the behavior of the internet so that we can predict some issues before they happen. So I'll go back to what I mean by some. So now, if instead of looking at the layer 3 only and being only reactive, you start using some machine learning algorithm, you may become, you may be able to do predictive in addition to reactive. So how are we going to do that? And I should say, by the way, how did we do that? Because these kind of technologies are now in full production with hundreds of customers. But at the beginning, I faced a lot of skepticism, which is a very nice. I think this is really the best way to start a project. You want to be skeptical from time to time. So first of all, we're not replacing reactive. We want to predict some issues before they happen. I also wanted to look at the layer 7 and find out brown issues as well, and gray layers. That's depending on your color of choice. You want to see that the path is degrading, and because it is degrading, the idea would be to say, I can predict that there will be a degradation of the SLA, and I want to reroute proactively before it does happen. And of course, for that, you may want to have self-healing networks. So let me show you this video. In this case, the technology has been applied to SD-WAN. And so we have a predictive engine in the cloud. This engine gets telemetry from an SD-WAN network using a SAS-based controller. So you don't add any extra overhead on the routers. You get the whole telemetry, such as BFD probes, telling you more about the delay, the packet drops, and the jitter. You can do as well some kind of deep packet inspection, the amount of traffic going from each point to another point, and so on and so forth. So if you take this example of this branch office, the job of this engine is precisely to look at the policy, determine, for example, in this case, that you may want to use MPLS tunnel to a data center to carry voice. You may want to use another internet tunnel, or for Office 365 application, you may want to do a local breakout, for example. So suppose that this is the default policy. The job of the predictive engine now is to model and compute the probability of SLA violation along each path for a given set of traffic and applications. Now, the job, if you will, of the algorithm is to do three things. One is for each remote site and for the list of applications of interest, you want to look at the probability of layer 7 SLA violation along each of the paths. If you find out that there is a high probability of SLA violation for the path that is set up as the default path for this application, and there exists an alternate path with significantly lower probability of SLA violation, and there is sufficient traffic along this path, because you may not want to do that for paths that do not carry any traffic, then you can raise an alarm that says, hey, I do predict an issue, there is an alternate path, and of course you take into account the fact that you are going to reroute on another path, and so on and so forth, and then take action on top of that. There are many types of predictions. Some of them are said as being short-term predictions for the next few hours. Other ones are long-term predictions. You can even use machine learning now to do real-time predictions about issues that are just about to take place, in which case, if you are predicting an issue in the next few seconds, you don't have the time to raise the alarm, make sure that there is a human in the loop to validate. Of course, you need to have a self-learning network. I could spend a lot of time summarizing the metrics, but what I chose to do is to show you one metric, not 10, but one. And in this case, what we're looking at is for 60 customers spread across 3,000 cities. We looked at the percentage of time there was an SLA degradation, SLA violation, should I say, and what was the percentage that would have been avoided thanks to the recommendation of a system. In other words, it's a sort of before-after. What we found out was that it was about 25% of SLA violation that could have been avoided by following the recommendation and the prediction of the system, which to me is way higher than what I was hoping for. My target was more about 5-10%, and we managed to do something way better than that. Okay, we talked about real time. I won't go too far, but you can even start learning some very specific patterns that may be specific to specific types of links and things like that, and detect this kind of motif as early sign of an issue that is happening later on. Okay, I talked about SD-WAN, but the same technology could be used for SASE when you connect to a given POP, for example. You may want to make sure that the system is fully predictive. And if you connect to the closest POP, or on the fly, you run some pings and you find out the closest POP to your source, if you will. You may want instead to use a predictive engine that says, okay, indeed, this POP A is the closest one in terms of delay, but I do predict some issues. If you are planning to use voice, for example, you may want to use another alternate POP that seems to be a little bit farther out, but that will overall provide a better SLA. We could do the same thing with home networking. I'm not going to spend too much time, but think about it. If you learn that your system is likely to be congested because of a Wi-Fi home network and the kids go back home at 6 p.m., that's a kind of pattern that the system is capable of learning, in which case you may want to start using 4G for a short period of time for some applications according to some policies. And we could do the same thing for the layer 7. I'm giving the example of App Dynamics, but for service providers, and I've been talking to many SPs in that area, we could apply predictive to optical networks, to cases where you want to make BGP predictive, and instead of using the BGP rules to select the best next hop, you may want to override it and start being able to predict issues and what is the best next hop for some destination at least. And we can do the same thing for pop selection as well. All right. So I know this is a lot of use cases and information, but I'm not done. I wanted to spend a bit of time on quality of experience. And I apologize because I'm going to be a little bit provocative, but I think this is important. So what about, looking at QE as we've been doing for 20 years? And the vision of the industry, and you may recognize this table from some RFCs 4594, is that what you're trying to do is to say, okay, how do I determine what should be the SLA for a given app? And what people usually do is to say, okay, for given multiple classes of applications, and we look at the sensitivity to loss, delay, and jitter. So in this case, you assign a weight, and then you will monitor in real time the loss, delay, and jitter, and you automatically compute a metric, and you call it the QE, or you provide some hard threshold, and you say for voice, delay should be below 150 milliseconds. So at 140, you're happy. At 160, you're not happy. And then you look at the jitter and you say, okay, it shouldn't be more than 50 milliseconds, and the packet drop should not exceed 3%. That's what people usually do. And this is, probably one approach, but I do believe this is far from being sufficient. And I would even say that is actually fairly wrong. And what drives the QE and the user satisfaction is not driven by static templates or some formula when you add a weight and you play a little bit with the values and you end up with a number between 1 and 5, such as the MOS score. So one very valuable and promising approach, which is known as cognitive networks. It's a very overloaded term, so I don't pay attention too much to the terminology. Might be to use machine learning to learn automatically. And if you remember what I said at the beginning, when I was mentioning about Wi-Fi and learning the threshold, what you may want to do is to basically look at what is actually driving the user satisfaction. So instead of using this magic formula that I was mentioning before within a sort of application health score, which is just a weighted average of some KPIs, you may want to look at the real feedback of users and learn using a model, using cross-layer telemetry. And this is something very close to my heart. As much as I love the dogma according which we should not do layer violation, which was extremely useful to scale the internet, it might be a good time now to revisit a bit this dogma. And with this kind of network, what you may be able to do is to look at the entire stack, take some data points in terms of telemetry across the layers, and I'm not just talking about the delay, the jitter, and the loss, but also the kind of codec you're using in all these things. And on top of that, if you can get some labels from a user giving you the subjective perception about the quality of experience, which could be as simple as good or bad, then the goal of machine learning would be to learn what drives a thumbs up or a thumbs down. And so we have done a lot of experiments. I've got a white paper, very detailed, on my website that you can find. And we conducted an experiment at a mass scale where we could show that it was indeed possible to understand what makes the user happy and not happy. And that was a very deep experiment. We could even determine the root cause, because now you have a model. And if you have a model, you can look at what is really driving the classification, such as good experience, bad experience. And there are many ways of doing that, so I won't go too far. But of course, if you can now really understand the percentage of user on a given site that's happy, you can start thinking about a feedback loop that would allow you to reconfigure the network with one objective in mind, improving the quality of experience. And we all know that what people do today is to look at the bandwidth and say, I'm going to increase the bandwidth. And you ask the question and say, by how much? And we just don't know. So we try to have a very empirical approach. In this case, it would be entirely driven by the query. And so we managed to show that such an approach was indeed very effective. We had up to 100,000 labels. That was very much sufficient to explain what could drive the user experience as well. I won't spend too much time on that QE experiment, but I think this could be a very promising path. And for us, networking people, it might be a good time to revisit a little bit our definition of QE. Okay, we've got about 20 minutes, and I think that we need to spare some time for Q&A. But still, I wanted to give you a glimpse into the future with generative AI. And of course, everybody has heard of generative AI since we started to see ChatGPT back in November 2022. So as always, you may remember my first slide, which was about starting with use case as opposed to starting with technology. And one more time, when you look at ML now, we do see a lot of people very much excited by generative AI for a good reason, which is that it opens up so many doors. Still, you may want to look at the use cases, right? What could we be using generative AI for in order to have a really strong value adds for networking? And there are basically three use cases that I wanted to discuss a little bit with you today. First one is natural language. In other words, instead of using the CLI that some of you may love, is there a possibility to interact with a network using natural language? And you may say, well, what's really the point? I know the CLI by heart, and it may be way faster to use the CLI than natural language. It's not always so obvious. And by the way, it could open a lot of opportunities, and we do see these opportunities as we speak. And you may start using natural language across, all of your platforms instead of having different CLI for different type of equipment. So this is really amazing what you can do with natural language. Second one is performance monitoring. So as of today, if you really want to understand how your network is doing, you may have your in-house application that is in charge of collecting some variables and thresholds and look at the behavior and so on and so forth. Wouldn't it be amazing to be able to have a system that will answer your question about performance monitoring, and such a system may have access to multiple controllers, multiple domains, multiple vendors, and all you would have to do is basically to ask the question to the system and say, are there any correlation between SD-WAN and DNAC and ThousandEyes, you name it, or whatever, or your preferred technology? It's not very important. You may even want to ask this question such as, is there any correlation between the quality of experience of a given application and the total amount of throughput, and things like that. So that could be a very interesting use case as well. And then the last one that I personally love is really about troubleshooting. And we all know that troubleshooting could be very cumbersome. In many cases, it takes some time to think about the root cause and start to do troubleshooting, especially when you go across layers or you go across domains. And it may require, in some cases, to go through multiple controllers, start to stitch information together until you find the root cause. I absolutely believe that with the help of generative AI, and I will not have a time today to focus on generative AI, but don't hesitate to reach out to me if you want to know more. I'm planning to post many videos, maybe go back to Nanog in a few months and do a very deep dive into the technology and how it could be used for the sake of troubleshooting. I do believe that this is one of the most promising areas, one of the most challenging and complex as well, but very promising. Okay, so this drives me to the conclusion. So what can we conclude? So yes, one can continue to design, deploy opera networks as we did over the past 20 years. There's no reason why you would not be able to do exactly what you have been doing for such a long time without any kind of analytics, machine learning, or AI. But at the same time, the benefits are undeniable. I really believe so. As I said before, I've been deploying this kind of systems, developing this kind of system for a long time. I've seen these systems deployed at very large scale, and the number of use cases is absolutely obvious. Anomaly detection. Remember what I said about Wi-Fi? Instead of configuring static threshold manually and potentially change over time, you can make this totally automatic. So why not doing that? If you look at predictive and forecasting, there is no alternative. If you're trying to forecast or predict a future event, there is no way you can do it without this kind of mechanism. And I showed you about the predictive internet. We have evidence now that it is possible for some issues. It is absolutely possible to have very high precision, and you just want to design a system so that you stop before starting to see too many false positives, but there's absolutely no alternative other than using machine learning. We may want to have a better understanding of application SLA. Finally, we've been postponing this exercise because it's a difficult one. I would encourage you to have a look at the white paper that I mentioned. This is a very promising area where ML could be one of the best tools you can think of. Automation, boy, we've been talking about self-learning, driving, you name it, networks for such a long time. This is a very difficult topic. You need to trust the system in order to automate. I haven't mentioned that, but I will in a few seconds. Just in a few seconds. When you do the predictive, we have 3 phases. Phase 1, the system will tell you that it does believe there will be some issues, and it does make a recommendation. Step 2, you have a human in the loop that says, I want to implement the recommendation. And everything is automatic, but you have a human in the loop. Phase 3, maybe that at some point you want to enable automation, in which case the system will take some proactive actions and will auto-monitor itself and will disconnect should it determine that it hasn't done a great job. So there are many safety nets that you can implement as well. And I finished the presentation talking about performance analysis, troubleshooting using generative AI. I absolutely believe that all of these use cases will expand to and apply to a number of domains. I talked about Wi-Fi. Sorry, I didn't have the time to talk about 5G, but LAN, data centers with AI workloads, for example, which is a very hot topic these days. The one I talked about it, optical SASE, multi-layer has been a recurring issue. This is also a very neat use case for machine learning. Just a few words of advices that I wanted to share with you. The first one is don't get trapped in terminology debates. And I see that all the time. People who say, oh, is it real machine learning? Is it really AI or is it machine learning? I do believe that it's absolutely non-important. And in some cases, a simple statistical model would just do the job. And a statistical model is not pure machine learning, but who cares? at the end of the day, it does the job. I would say to people, resist to waves and overstatements. We keep talking about AGI these days. We don't even know what is AGI. So I think that a bit of nuance is useful. And when people talk about generative AI, it is highly promising. We start to see some excellent results. But at the same time, we need to be a little bit cautious about it because there will be disappointments down the road. And this is always the case when you have overstatement. Handle the pace of changes carefully, because it's probably one of the first times, thanks to open innovation, that we see the technology moving so fast that it's getting difficult to stabilize a product. I'm just about to release a blog on that as well. I would say apply the appropriate technology to the right problem. Don't jump on the latest and greatest algorithm. The barrier entry keeps going down, which is great. At the same time, there are major challenges that people need to be aware of, such as system performance metrics. When you look at the system, like generative AI, people tend to look at the algorithm performance. It's one of the components of the system. You may want to look at the holistic performance of the system. I also posted an article discussing about that. Okay, so what's next? Well, AI and generative AI will continue to evolve at unprecedented pace. I don't know what's going to come next, but there's no doubt that it will continue to evolve. I strongly believe that ML/AI will continue to spread across domain and layers. As I said before, there are many low-hanging fruits like anomaly detection and predictive. And I think that the next challenge will be about self and troubleshooting. So self-improving technologies is a difficult one. It's not ready for prime time. That's probably the same for troubleshooting, but this is where we can leverage some sophisticated ML/AI system of the best of the network. All right, so I was about to do it in 45 minutes. It has been 47 minutes. With that, I think that we are ready to take some questions, should there be any questions. So let me maybe stop sharing. I don't know if we have anybody on the call who is ready to read some questions that we have received. Okay.
Yep. Thank you, JP.
Thank you very much.
I do believe we have a couple of questions here, so please go ahead.
Hello, my name is Reza Rukui from Siena. Nice presentation, JP. One question that I have to ask you, and I think you didn't mention it, putting generative AI aside, all these use cases that you mentioned, at the end of the day, you define or design a model and you have to train it. Where is the training data coming from? Because in most cases, you need those from operators, and there is no incentive for operators to share those because of various reasons. So, and you need a large amount of data to have a model which is reliable enough to use it. So if you can touch on that one, it would be great. Thank you.
Yeah, thank you very much. This is very much true. So first of all, maybe I can say a few words about the amount of data, but also the quality of the data. So you're right that maybe carriers and telcos may not always want to share publicly because that's part of some proprietary information. So in this case, what they can do is to train their own algorithm on the side. As a vendor, talking for Cisco, we have access to a lot of data, and we can basically remove everything that is private and proprietary and still do a lot of training. So for example, if you look at Wi-Fi that I mentioned before, it's exactly what we do. We take the telemetry from hundreds of thousands of access points. We curate this information because we don't have access to the private information. And so because of that, we have a telemetry coming from so many enterprise networks, and we can train the model with a massive amount of data. The same strategy can apply to many other domains. So now, just to say a few more words about the telemetry. What people used to say is we need to have a massive amount of data before we can do any kind of work related to machine learning. I think that we need to look also at the diversity, because when you train a model, you want to make sure that the model has seen diverse data, and also quality is also very important. So if you look at the classic machine learning, most of the time, my recommendation would be, hey, spend a lot of time removing the noise, so it doesn't require quite a bit of work. You said, aside from generative AI, for generative AI, you might have heard of something called textbook is all you need. So it's basically to say, these generative models have been trained on trillions of tokens from the internet. In some cases, you may see some pretty much equivalent capabilities on smaller data set, as long as the quality of the data set is extremely strong, if you will. So the quality is also important. It's not exactly equivalent, but you can do some interesting work. I know your point was more about how would SP share the data used for training.
When I said putting a generative AI aside, because in most cases you're not training the model is already trained with the billions of the input and output before, and you are using it. And in some cases you do the fine tuning. This was the reason I say for that aspect, you keep that one aside. Other model, you have the model is empty, you have to train it. And this was the reason I tried to make a distinction between generative AI and non-generative AI. Thank you very much.
Yeah, thank you.
All right. In the interest of time, I think we need to basically go to the next presentation. So thank you for your time, JP.
Thank you very much. Enjoy the rest of the night.